blog, and the main motivation was to encourage the electronic students to take the research forward and try to get research done at BITS and try to teach that. That's what I'm going to try and do in the next hour or so. So this is the agenda. This talk about me. She covered quite a bit of it. This will be summary. Then I'll talk about my research. I've been working on radiation effects in the last 2 years in cosmic and then me and one from BITS Goa, and we guys worked on this for 2 semesters. So that was there then. So because of this liberty and no deadlines, we had all the time in the world to do in-depth study of every aspect related to radiation effects. So I read more than 150 papers, which are very helpful. I work in a small 4 members which are coming from outer space. Now what happens is, so this is a MOSFET. This is an NMOS actually right now. And so what happens is when the neutron comes, it goes inside the P substrate here, and it strikes the nucleus. Since neutron does not have any charge of its own, after it strikes the nucleus with a lot of force, it generates tons of ionizing particles like this, electrons and protons in all directions. So what happens is these electrons and holes now go towards the drain and they get collected by the drain. And if a drain was earlier storing, let's say, a value 0, let's assume that this drain belongs to a memory cell, and the memory cell was storing a 0. If you inject holes in it, suddenly you can make it go to a 1. So now if the number of holes here injected after this strike are large number of holes, then the drain can flip from 0 to a 1. And if a memory cell flips, it can cause a lot of different problems. I won't go into that. So during operation, a memory cell flipping is not a good thing. So this event which I described, this is specifically called single event upset, and that's maximum energies here of the particles can go to very high values, 128 MeV, and whereas the maximum energy on Earth, which those particles get absorbed in the atmosphere, and whatever is left, they can maximum have an energy of 15 megaelectrons. So that's a big difference. And then the other thing is the flux of the particles in space is way higher. There are much more particles there. A lot of them get absorbed before coming to Earth. So flux is very high in space, and flux is only 10 to 50 particles per centimeter square per hour at sea level. So now SEU protection in aerospace defense is a common practice for decades, because there you have such huge particles coming in. So the bigger the particle, the more electrons and holes it can deposit in the device. So earlier on, for let's say more than 100 nanometer generation, the amount of charge stored at each node is just a simple Q is equal to CV. So this C is reducing with every generation, and this B is also reducing with every generation. So earlier on, both of these were pretty high. So on Earth, we didn't care about 50 MeV because it wasn't strong enough to cause any problems to this Q. This is what the present is. It's the top level picture that I'm giving here. So most of the electronics industry is presently using 45 to 65 nanometer technology node. So this is what has been produced, which has been given to the customers, and it's in use. It's in your phones, it's in your routers and all, right? But 28 nanometers is at the end of its production cycle. So within half a year to 1 year, you will see 28 nanometer products in your phones and your routers. And the designing for 20 nanometer node is already underway. So that's part of the process. So that's the next node, which the time scale for that is in another 2 to 3 years. We will have the next node, which is 20 nanometer. So at one time, some said that there's no way that you'll be able to go below 1000 in nanometers, and we're already at 20, and there's a roadmap till 6 nanometers of it. So yeah, the electronics industry, there's too much innovation, and whatever seems impossible somehow gets done by some or the other genius. So this is what in FinFET, your height of this cannot change, and that is what is defining the strength of your transistor. That's your W by L. That's the W in your W by L equation, the height of this. In this, the W was the width of the source and the drain, which was pretty big. So that did. This is the width in this case, which can scale according to whatever you want. This is source drain. This is the width of the transistor. Now the width is this, and you can't make it higher in one side, lower in one side. You have to replicate it like this. This is a figure from Intel's FinFET 22 nanometer. And this is another figure which explains it in a slightly better way. You need to have the source and drain very thin, because you need to have you need to provide maximum control over source and drain voltages. So you need to have it as thin as possible. This is what it does. So all the problems in planar technology related to leakage, this is how it solves all this. So this is your channel current, normalized channel current, and this is your tri-gate technology, this is your old technology. So it reduces by a factor of 10x, 10 to the power minus 4 and 10 to the power minus 5. So it reduces by a factor of 10x. So that's a big reduction, and your on current remains the same. Your difference between this and this is now much bigger. So on and off are well-defined states in FinFET. And this is your delay. So delay is also getting better because gate has more control. So more electrons and holes can flow through from the drain and the source to each other, and hence it also makes things faster. So at the same voltage, you can have much faster things. So if you want power reduction, you do this. You use lower voltage, so you will get same performance. If you want performance, you use the same voltage, you get lower delay.